Good morning, friends. I am Dr. Munish Bharadwaj. Yesterday we were discussing about block 2 of operation and maintenance. In this block we discussed about introduction to power system and unit 6, which is distribution transformer. Another unit which is also very important unit in this block of operation and maintenance is substation equipment and distribution lines. So today we will be discussing about this substation equipment and distribution lines. Today we have with us Mr. V.S. Verma. He is member planning, Central Electricity Authority, and next to him Mrs. Anjali Chandra. She is Director, Central Electricity Authority. Yesterday we got very good response and very good live interaction with the students. I hope similar response and interaction today also. Whenever you feel any problem, if any doubt comes to your mind, then you are free to ask question at any point of time. With these words, I would like to request Mrs. Chandra to initiate the discussions on the topic.
Good morning, friends, and welcome to this session on substations and lines. We are going to discuss about the equipment associated with substations as well as the lines. We'll take the substations in two parts: the primary substation, that is the 33 by 11 kV or 66 by 11 kV substation, and the distribution substation. So first we'll go to the primary substation, that is the 33 by 11 kV or 66 by 11 kV substation. This is a picture of a 33 by 11 kV substation in J&K, and you can see what it looks like. We are going to discuss the various equipments installed in this substation. So the various main substation equipment are the power transformer, the bus bar, the switchgear, the structures, the control protection and monitoring equipment, the earth mat, the automation system, and the site support facilities. We are going to discuss each of these in a slightly greater detail. So the power transformer. This is the most vital and costliest equipment of a substation. The power transformer can be 3-phase or single-phase based on transport limitations. It's generally a 2-winding transformer, and it has an on-load or an off-load tap changer for changing the voltage which is coming at the bus bar terminals. These tap changes are in the range of plus minus 2.5%. The preferred transformer capacities for primary substations are 6.3, 8, 10, 16 and 20 MVA for urban areas, and 1.6, 3.15 and 5 MVA, and now also 6.3 for rural areas. Not to say that other ratings cannot be used, but these are the generally preferred ratings by most of the power utilities in the country. This is the example of a power transformer again. You can see that.
Can you explain a little bit more the function of the tap changer you said?
The tap changer is being used by most of the utilities to maintain voltage at the 11 kV terminals. For example, if we get lower voltage at 33 kV, then by increasing the tap by operating the tap, we can go to plus voltage. The tap changer is a device which changes the voltage in steps. So these steps are specified in IS 2026.
These are towards the output secondary side or the primary?
On the primary side.
On the primary side.
Yes. So you can change the voltages of the voltages available on the 11 kV side, and this is mostly because in our country the voltages are low. The voltage from the grid itself is low. So when it comes to 33 kV, if you don't operate the tap, then your voltages are going to be low on the 11 kV side. And as you know, the problems associated with low voltages are that we have higher losses, we have low voltage profile, we cannot maintain the voltage at the consumer end. In today's day of regulation, we have to maintain plus minus 6% at the consumer terminals, but we would not be able to do this if the voltage from the grid itself is low. So the tap changer helps in maintaining the voltage to the desired voltage level. Then we have the bus bar and the substation. That is a conductor for the main or transfer bus and for equipment interconnection. This bus bar can be of triple AC conductor, ACSR conductor and double AC conductor, or can be made of aluminum pipe. And the space for a bay, it depends on the face to face clearance, face to earth clearance and the safety clearances required. We always talk of 33 kV bus and 11 kV bus, where all the feeders, incoming feeders are terminated and the outgoing feeders also emanate from a bus. So the bus bar can be of any of these conductors depending on the size and rating of the substation. The size of the bus bar will depend upon the current it has to carry. The bus bar will have many schemes like single bus bar scheme, main and transfer bus bar scheme. You have various schemes, but generally in this we have double bus bar or single bus bar in 33 by 11 kV substations. Then the next important equipment is the circuit breaker. The circuit breaker is an on-load mechanical switch used for making, carrying and breaking currents under normal conditions and breaking under abnormal conditions. These circuit breakers can be of many types. It can be an air brake circuit breaker, an oil circuit breaker, a minimum oil circuit breaker, air blast circuit breaker, SF6 circuit breaker or a vacuum circuit breaker. Earlier bulk oil circuit breakers were being used, but now these are being phased out and we are generally using vacuum or SF6 circuit breakers. The SF6 breakers have an environmental impact and they should be very carefully used so that there is no leakage of SF6 into the environment, because the global warming potential of an SF6 gas is around 24,000 times that of one carbon molecule, so carbon dioxide molecule. So we should be very careful when we use SF6 breakers.
What is the function of this gas in the circuit breaker, likewise oil or air blast?
It is an insulating medium because the arc generates a lot of heat, and to dissipate the heat we require an insulating medium inside the circuit breaker.
Oh, conducting actually insulating.
Yeah.
I mean this just to dissipate the heat absorption.
In the circuit breaker. The operating mechanism of the circuit breaker can be hydraulic, pneumatic or spring type. Then we have the isolators. You must have all seen isolators in a substation. The isolator provides a visible air gap isolation of equipment and feeder sections for safe examination, maintenance and repair. It is capable of carrying normal current and short circuit current for a small specified time. The various isolators are horizontal center break, double break, pantograph or vertical single break. The earth switch of an isolator the isolators also have an earth switch, and the earth switch of the isolator is a mechanical switching device for providing safety earthing during maintenance. It is capable of withstanding short circuit current for a specified time. Then we have instrument transformers. We have two types of instrument transformers in a substation: the current transformer, commonly known as the CT, and the potential transformer, which is known as VT or PT. These are, for the current transformer, these are the devices used to get a replica of primary current, which shall be suitable for measuring instruments and protective relays. We have meters inside a substation, and the meter cannot withstand the current generated in a substation. It either takes 1 ampere or 5 ampere. So the current transformer is used to transform the current in the substation for measuring purposes to the level which can be taken by the meter, which is 1 ampere or 5 ampere, and it also takes the current to the protective relays. The relays operate whenever there is a fault in the system. So these relays also operate at a lower current level, and the number of cores in the CT depends on the requirement. There will be a metering core, there will be a protection core. So we have the cores as per the requirement. The instrument transformers, the second type of instrument transformer is the potential transformer or the PT. These are devices used to get replica of primary voltage which shall be suitable for measuring instruments and protective relays. CT gives the current and PT gives the voltage for measuring and protection, and again the number of cores in the potential transformer are as per requirement. Then we have the surge arresters in the substation. These surge arresters are made of zinc oxide disc and provide the primary protection against overvoltage caused by external sources like lightning and by system disturbances. These are designed with respect to energy capability and pressure relief capability. Then we have shunt reactors in a substation. These shunt reactors are used to provide reactive compensation. As we know, the loads in the system, especially at the consumer end, are inductive, and they draw inductive current from the system, which makes the power factor low. Therefore, we have to use shunt reactors for compensating the reactive power draw from the system. If we don't compensate, then the reactive power draw will come the entire way from the generation. The kVA demand will be much more and your losses will be much more. Therefore, we provide shunt capacitors at the 33 by 11 kV substations or the 66 by 11 kV substations. These are generally provided on the 11 kV bus of the substation. So, and these control dynamic overvoltages as well as reduce the losses and improve the voltage profile of the system. But generally people have an hesitation of operating the capacitors. Our experience has been that though the capacitors are installed in the substations, they are mostly not operated, or because these have to be either automatic type or switch type. The automatic type get switched on and off automatically, but if they are fixed type, they'll remain in circuit and give compensation which is equal to the base compensation. Then we have control and relay panels. If you have seen a control room, you will see there are control and relay panels in the control room. There are relay protection panels for transformer protection. The protection given to a transformer is differential protection, overcurrent and earth fault protection, and restricted earth fault protection. For a shunt reactor, the protection could be differential protection, overcurrent and earth fault protection, and restricted earth fault protection. And for a sub-transmission line, the protection could be one main protection and overcurrent and earth fault. Generally, we are using overcurrent and earth fault protection. We have the control, relay and protection panels in a control room building, the batteries, the battery chargers, the main switchboard, the AC distribution board, the DC distribution board, the lighting transformers, lighting distribution boards, rooms for station in charge and staff, and other miscellaneous equipment.
What is the role of batteries here?
Battery is to provide the input for the indications for the system.
Control system.
Control system
is okay.
So we have the earth mats inside in a substation. The earth mat is provided for safety of the living beings around the vicinity of the substation, proper functioning of the protection system under fault condition, and to limit the touch and step potential within tolerable limits. You must have seen earth mat as whenever the construction of a substation is started, then the earth mat is provided in the switchyard. For safe design, EM should be less than E-touch and ES should be less than E-step. The station battery is a source for operating.
Can you explain EM, E-touch, etc.?
So there is touch and step potential. When a person is in a substation, then if he touches something or the step potential, that should be within limits. These limits are specified in IS again, so that when you design the earth mat, then your limits should be maintained. So you take into consideration the size of the flat, the entire resistance which comes in the circuit. So that resistivity, what should be the resistance of a earth mat, that is defined in IS. And the design is also specified. The station battery, as we were discussing, is a source for operating control system equipment during system disturbances and outages. Normally 24 or 30 cells consisting of lead acid or nickel cadmium batteries are used in a substation for battery purposes. These are the major equipment. Then we have the firefighting equipment, we will have a fire extinguisher, we have lighting equipment. So all these are also available in the substation. These are auxiliary equipment which are required in a substation. Then we come to the distribution substation. Distribution substation is what we call for the 11 by 0.4 or 33 by 0.4 kV distribution, for having the distribution transformer and associated equipment. The distribution substation consists of the distribution transformer, its mounting structure, lightning arrestor, LT distribution box, protection system, LT cables and reactive compensation for the distribution substation. The transformer can be mounted outdoors in one of the following ways. It can be direct mounting, it can be plinth mounting, it can be edge structure mounting. Inside, of course, you are going to mount it on a plinth only, but outdoors you can use these three types of mounting for the distribution transformer. You have seen many transformers mounted on the roadside. They will be on either edge structure or a single pole. So direct mounting we will discuss first. The transformer is clamped directly to the pole by suitable clamps and bolts. This method is used for transformers up to 25 kVA only, because they will the single pole will not be able to take the weight of a transformer more than 25 kVA.
But in the HVDS system, which yesterday you covered, and you are providing to reduce the losses as well as to make the supply reliable, do you think that the transformers of more than 25 kV would be required?
No, in HVDS the basic concept is small capacity transformer. So in fact in REC people are thinking of going in for 5 kVA for small hamlets and villages, and otherwise also the concept of HVDS is that you give power supply to not more than 10 consumers from a single transformer. So the rating will not be more than 25 kVA. If it goes beyond that, then it is not an HVDS, because in HVDS we want to reduce the length of the LT line.
Yes.
So it will either be 5, 10, 15, 16 or 25 kVA, depending on whether it is single phase or three phase.
And they will also be pole mounted.
They will be pole mounted. Mostly they will be pole mounted, but you can have plinth mounted also. There is no bar on not having plinth mounted. But the smaller the size, you can easily have it on the pole.
But if you have a large number of such transformers in a colony, for example, then don't you think that the cumulative losses, individual sum of the losses of these transformers could be more than the one large transformer which you provide?
Definitely the iron and copper losses will be more, but the transformation losses in any system will not be more than 2 or 3%, whereas the technical losses in the line will be much higher. And the reduction in losses on account of reduction in line losses will be far more than the small increase in the transformation losses.
I see.
So therefore, transformation losses do play a role, but the small increase in transformation losses will be far compensated by the reduction in line losses.
So typically there would be about 2% losses in the transformation?
Yeah, 2 to 3%. Yes, in HVDS it will be slightly more because the number of transformers is much more. For example, if you have a 63 kVA transformer, you might have to replace it by 5 into 25 or 4 into 25. So the number will be higher because you can, when you distribute the transformation capacity, you don't load each transformer more than 70%. You keep a margin. So margin in one transformer and margin in 5 transformers means you will have to keep more transformation capacity. So your iron losses and copper losses will definitely go up. But your reduction in line losses is far compensating for the small increase in.
Now, if the transformer is not overloaded, I am asking this question because now in HVDS you provide a large number of transformers.
Yes.
In say 4 or 5 houses clubbed together and fed by one transformer. Now, what would be the failure rate of these transformers, because the maintenance will become absolutely unmanageable.
Yes.
If the maintenance is more and repairs requirement are more.
Well, you know, up till now, whatever transformers have been installed, because they are not being overloaded, and the LT faults are much less. Most of the transformers fail on LT faults. If you see, yesterday we had discussed the transformer failure. The failure is, it has been observed that 65% of the failure is due to failure of the LV coil. And that the LV coil fails mostly due to failure of the, due to failure in the LT system, due to overloading and things like this. So when we use HVDS, we do not overload the system because there are 3 or 4 customers only on that transformer, and they themselves see that there is no hooking. You know, overloading is mainly caused by hooking, and if there is no hooking, then there will be no overloading. So the transformers are less likely to fail. They may fail on manufacturing defects, but then that happens with either single HVDS transformer or a 3-phase LT distribution transformer.
But this fact has already been taken into consideration?
Yes, this fact has been.
If the transformer goes out of operation due to some reason, some failure, what is the alternate arrangement for alternate supply made? Or till it gets certified, till you cannot do anything?
Mostly, you know, you wouldn't be providing ring main unit for small capacity transformers, so it will have to wait till it is rectified. Ring main units are generally provided where, you know, there are higher capacity transformers. It would not be economical to provide a alternative supply.
And would you keep the spare transformers in the stores of distribution?
Yes, definitely. In HVDS, you should be very particular about creating an inventory for the transformer. But actually, when a transformer fails, when only 3 or 4 customers are being affected in a small capacity HVDS, whereas in a LT distribution system, if a bigger transformer fails, then hundreds of customers are affected. So, you know, the relative effect of a failure of a transformer is much less.
No, 3 or 4 customers are affected with that transformer.
With that transformer.
Now, the bigger transformer has been replaced by maybe hundreds of transformers.
Yes.
Like this.
So, if 2 or 3 fail also, then the number of customers affected will be much less.
Anyway, customer is important.
Customer is definitely important, and we definitely advise that you should keep an inventory of the small capacity, and it's quite easy to erect because single transformer with a single bolt, it's much easier to erect a new transformer.
Now, don't you think that you may have to develop the repair facilities in the country for such a large number of inventory of the transformers?
The transformers, when the volume increases, definitely you will have to have more of repair capabilities, but they should not be failing. We should also ensure that the specifications are such that these transformers do not fail very substantially.
Nevertheless, the failures will be there.
Failures will be there, and we have to have repair facilities. That is
no, I am asking this question whether the government or the utilities, state governments are they taking any action in this regard to develop the more repair facilities?
Yes, they are taking action, and they have been advised to do so also. So you can see in the picture the single pole mounting of direct pole mounting of distribution transformers of HVDS. You can see whether it is HVDS or it is LT distribution transformer. Transformers up to 25 kVA can be mounted directly on the pole. Then we have the H-pole mounting. This is most commonly used by most of the power utilities. The transformer can be mounted on cross arms fixed between two poles and which are rigidly fastened to the poles. The transformer has 2-number base channels which rest on the transformer mounting structure. You can see the H-pole mounting of a distribution transformer here. This is quite commonly used for ratings up to 250 kVA or even 400 kVA. 250 kVA is generally being used. They are mounted on H-poles. Then we have the plinth mounting. The transformer is mounted on a plinth made of concrete. The plinth has to be higher than the surroundings. The method can be used for all sizes of transformers, small capacity as well as large capacity. Where the distribution substations are plinth mounted, they should be efficiently protected by fencing so as to prevent access to the apparatus by unauthorized persons. Generally, it has been seen that fencing is not provided, but as per rules, you should prevent access to the distribution transformer when it is plinth mounted. You can see this photograph of a plinth mounted distribution transformer. So when the transformer is plinth mounted, one must provide facility for fencing the transformer or for isolating so that nobody can touch the live equipment. That will be very important. The distribution transformers can be single phase like for HVDS or 3-phase. The single phase transformers have a capacity of 5, 10 or 16 or 25 kVA. The 3-phase transformers may have a standard rating of 25, 50, 63, 100, 250, 400, 630 and 1000 kVA. These are the preferred ratings, but other ratings can also be used. Then we have the lightning arresters. Yes. Gopal, please speak.
Hello.
Yes.
Hello.
Please.
Hello.
Ask your question, please.
Yes, Gopal.
Hello.
Ask your question.
Hello. ये 33/11 kV का ट्रांसफॉर्मेशन का लाइन लॉस का परमिसिबल लिमिट क्या है?
Line. You want to know about the line loss or the transformation loss?
नहीं, sorry, ट्रांसफॉर्मेशन लॉस.
Transformation loss. Okay.
परमिसिबल लिमिट बताइए.
Permissible limits. Actually, it depends on the efficiency of the transformer. The power transformer generally has an efficiency of 99%, and the transformation limits. Actually, the transformation limits are set for the line as well as the transformer together, and they are 2 to 2.5%.
There is total line.
Total line plus the transformer. I think the loss in the power transformer should not be more than 0.5%. Does that answer your question?
Yeah, that's it.
So we'll move to. We were talking about distribution substations. The distribution substation should have a lightning arrestor to protect it. The 11 kV lightning arresters should be installed of 9 kV rating, outdoor type, for diverting the lightning surges to earth. The resistance of the earth and lead should be minimum, and the lightning arrestor should be installed on the HT side of the distribution transformer. Then the distribution.
What is the danger if the lightning arrestor is not installed?
If the lightning arrestor is not installed, then the transformer may fail whenever the lightning strikes the distribution transformer.
Okay.
And it's more likely to be attracted to a distribution transformer, so one should install lightning arresters. Though generally people skimp on these things, they only install the distribution transformer, they don't install the protection or the lightning system. But we advocate that we should have a adequate protection and lightning arrestor on the.
But is there a guideline appearing from CEA?
Yes, in the construction standards we have clearly indicated what type of protection should be used. And these draft construction standards have been put on the CEA website under, you can see these draft construction standards at cea.nic.in, that is the name of the website. And if you go, once the CEA website comes, then you go under draft regulations or under regulations, then under draft, you will see the draft construction standards which clearly indicates the type of system to be provided for a 33 by 11 kV substation and a distribution substation.
Going by those standards, would they provide a complete guideline for the distribution utility?
Yes.
How to go about it, what kind of equipment is required, what are their specifications?
Not the specification of the equipment, but what kind of equipment is required. Specifications have been separately put under these regulations. There are draft specifications for the distribution transformer, but they are only for the distribution transformer, not for other equipment. We have prepared those and put them on the website.
Yes, Allahabad, please ask your question. Yes, Allahabad, please ask your question. Allahabad, please ask your question. I think line is disconnected.
Provisions for maintenance of lightning arresters.
We could not hear your complete question. Please repeat. Please repeat your question.
Can you hear me, sir?
Please repeat your question.
What are the codal provisions, if any, for maintenance of lightning arresters?
Codal provisions for maintenance of lightning arresters.
Code, any code.
Provisions in the code.
There are codal provisions for maintenance of the lightning arrestor, but generally the lightning arrestor consists of discs, so you should keep the disc clean and the connection should be maintained. There are no other provisions for maintenance of the lightning arrestor. It's a very simple piece of equipment.
But there is a Bureau of Indian Standards, BIS.
Yes.
Have they specified any such?
No,
things?
sir.
No?
Actually, this is an equipment which is like if you install it, then it just consists of this porcelain discs or ZNO discs, and there are the only precaution you can take is maybe keeping the discs clean.
No, I mean unless some direction is given.
Yes.
In this direction, everyone may not follow such instructions.
We'll try to see and give some directions on this. Well, the protection, when we were talking about the protection system for the distribution transformers, generally what we have observed is that even circuit breaker is not provided for distribution transformers, but the HT side of all distribution transformers is normally protected by dropout expulsion type fuse. 3 number 11 kV dropout fuse unit comprising a set are installed on mounting cross arm. The fuse element is soldered on the both ends between woven wires, which is sufficiently strong to take tension when fixed to the terminals on both ends. The element is housed in an insulated tube of paper or insulating material. For transformers of 100 kVA and above, suitable high rupturing capacity cartridge fuse or circuit breaker, MCB or MCCB or air brake switch should be provided on low voltage side. For high voltage side, dropout expulsion fuse. For low voltage side, for transformers of 100 kVA and above, MCB or MCCB should be provided or air brake switch. For transformers below 100 kVA, switch fuse unit or wire fuse should be provided. So generally when you provide a wire fuse, you tend to put a higher size fuse. Then the transformer will definitely fail. The fuse wire should be of a size that it ruptures whenever there is some fault on the LT side. So one should ensure that and not put a very thick fuse so that it doesn't burn at all when there is a fault on the LT side. Then reactive compensation, as we were talking about reactive compensation on the 33 by 11 kV substation, we should also provide reactive compensation on the LT bus of the distribution transformer. It is best to provide reactive compensation on the load end, but if it is not provided, then the next best is to put it on the LT feeder or on the distribution transformer. It should be provided on the LT bus of the transformer. Earlier the types of capacitors available used to fail very badly, and there was no maintenance of capacitors on the distribution transformers. But now the quality of capacitors for the distribution transformers has improved, and we can provide capacitors. They can be of the fixed type or the switch type. Generally 1/3 of the capacitors are 1/3 of the capacitor rating is provided as fixed capacitors, so that there is no overcompensation during off-load period. So quite a few utilities are providing capacitors on the LT bus, 25 kV, kVA transformers, 63, 100 kVA. We are providing 9 kVR, 18 kVR capacitors. You could also have switch type, which sends either the voltage or the current and automatically switch on and off depending on the reactive requirement. So both types of capacitors can be provided on the LT bus of the distribution transformer for compensating the reactive load in the system. Providing on the LT bus of the distribution transformer is better than providing on the 33 by 11 kV substation. So we should all install capacitors on the distribution transformer itself if it is not provided on the load end.
Perhaps there is a query from the floor. Yes, you can ask your question. Speak a little loud.
What is the difference between lightning arresters and the surge arresters, and where they are installed?
Lightning arrestor is mostly the term used for distribution transformer, whereas surge arresters on higher voltages, like 33 and above. Is it clear?
This would you explain a little bit more detail the reactive compensation? Why it is required? How does it help you? And in what form do you provide this reactive compensation?
Okay, actually reactive compensation is required because you have inductive load on your system. The inductive loads, for example, most of the loads on the system are inductive. The motors, the ACs, the compact lamps, CFLs, the fluorescent tubes, all these loads are inductive. They go in.
Yes. First we will take this call. Yes, please ask your question, Bombay. Yes.
Hello.
Yes, please speak.
Raghav is speaking from Mumbai.
Welcome.
I would like to know what on which side, whether LV side or HV side, the common faults are occurred in distribution transformers, and what is the reason for that?
Okay. Well, first we'll answer the question and then we'll move on to reactive compensation. The faults are generally in a distribution system are occurring on the LT side. Most of the faults are observed on the LT side. Generally the HV coil doesn't fail much. The LT coil fails, and most of the faults, 65% of the faults on a distribution transformer occur on the LT side. These can be due to fault on the line, due to maybe a tree falling on the line, maybe birdage on the line, or fault on the LT, any other fault on the LT line, and these faults reflect on the distribution transformer. Or this could be due to low oil level. There are very many reasons why a fault occurs on the LT side. So the transformer generally fails due to fault on the LT side, leaving aside manufacturing defects and other things. I hope this answers your question.
You were explaining reactive compensation.
Yes, we were talking about reactive compensation. So as I was saying, most of the loads on the system are inductive in nature. Now they draw in inductive current from the system. This current either has to be generated from the generating substation. But actual power being used in the system is the kilowatt hour component. So you should try and reduce the inductive component. If it comes over from the generating system to the load end, then your kVA requirement will go up, your current will go up, your losses will go up. So what you need to do is generate the compensation for this inductive current as close to the point of load where it is required. So to compensate this inductive requirement, we provide capacitors. This capacitor is in a direction, the KVR is in a direction opposite to that of the inductive requirement. So that is why we provide capacitors. But generally, as you see, all the consumers do not provide capacitors in their homes. It is only the industrial consumers which provide capacitors in the industries. So the cumulative requirement is compensated by the utility either by putting capacitors on the LT feeder or by putting it on the LT bus of a distribution transformer, or by putting it on 11 kV feeder, or by putting it on the 11 kV bus of the 33 by 11 kV substation.
Reactive compensation, can it also come from the generating machines if they are operating in different mode?
Yes, it can come, but then it would be very uneconomical to bring the reactive compensation from the generating end. It would load the machine more, and your losses in the entire system will occur in the transmission system, in the transmission and in the distribution system. You want to ask some? Yes. Okay, you can ask the question.
Should we install capacitor at the consumer end to compensate for inductive load of the consumer?
Yes, it would be advisable.
Have you any thumb rule to indicate what amount of capacitor, what level of capacitor should be installed at the consumer end?
Usually, you should install capacitors at the consumer end, but it is very difficult to assess the inductive requirement of the consumer. But the thumb rule is that generally the requirement is 1/3 of the total KVA load of the system. But then you should install actually automatic power factor controller, because the consumer does not know about the inductive requirement and he will not be able to control the capacitors. So if you can provide an automatic power factor controller, it would be better. It is more expensive.
It will reduce his bill also, no?
It will not reduce his bill, because at the moment billing is done on kilowatt hour. If the billing is done on kVAH, then yes, it will reduce the bill. Because LT industry is being built on kVAH in Delhi. There it will reduce his bill, but in a consumer, the billing is done on kilowatt hour. It will benefit the utility.
And for industries?
For industries, it will reduce his bill if the bill is on kVAH, or if there is a power factor penalty, or the demand is being assessed in kVA. Then his demand in kVA will come down. But for an ordinary consumer, his bill will not come down. That is why the consumers do not install capacitors, because his billing is not taking into account the reactive power at all. We don't have kVAH meters, we are installing kWh meters. So
we measure in kVA.
Where you have measure in kVAH, for example, in Delhi the billing is done on kVAH for LT consumers, there it will make a difference in his billing. Or where the maximum demand is being assessed in, maximum demand charge is being put in kVA. There also the kVA demand will reduce, his bill will reduce of the maximum demand related billing. Two-part tariff is used, kWh plus maximum demand on kVA.
But in industry, is it compulsory to have this compensation installed by the industry on their motor?
So there is an IE rule of provision that the power factor should not be below a certain level. So, and most of the utilities are having a penalty for having low power factor. So, though it is not compulsory, the consumer can pay penalty, but then it is in his interest to put a capacitor.
So thank you, Mrs. Chandra, for the nice discussions and live interactions from the learners, from the learner side. We will continue this discussion in the next session. We will meet now at 10 o'clock. Thank you.